that you can have done 4 years of physics before you start with something. But for them, it's like the half of their age or something like that. I invited them to come over, but I'm not seeing them here.
Oh man, that would have been great.
Okay. Yeah, I was already saying to some of you when we started that part of what I'm going to tell today is something that some of you have already heard in some capacity or another. It's going to be special relativity, but the special relativity that I'm going to show you is special relativity formulated in a different mathematical way. So it sounds familiar, right? We just finished the electrodynamics course where I also had to make use of this notation. I'm going to do exactly that. So some of this is going to be very familiar to some. But it really pays to really pay attention to what happens there, because all of general relativity has to be written in this particular mathematical formalism. Special relativity you can do in multiple ways. General relativity you can only do in one way. So even if you already know special relativity by heart, you know everything about that, even if you already know the notation, it still pays to see what I'm going to do, because I'm going to use the exact same formalism starting next week, and then do general relativity with only minimal mathematical extra stuff added to it. So that means all of the mathematics, quote unquote, is going to be today. Now, just to be sure, of course, there's going to be mathematics in the other weeks, but what I mean is that the application is something from next week, but the actual build up of the mathematics is today. With only minimal change, we're going to apply everything we're going to do today to general relativity starting next week. So today is just special relativity. Now, I guess everybody, and I think it's a prerequisite of this course, has done special relativity. And it's a theory that is by itself highly interesting, but unfortunately it also comes with misconceptions. It's very easy to misunderstand special relativity, even if you know the formulas by heart. So the tutorial exercises are almost exclusively going to be about, here's some situation seen by some person, and what does the situation look like seen by some other person who is moving with respect to the first person. Because as you remember from special relativity, this is what special relativity does. If you know how physics looks to some person, and you happen to be that other person moving with respect to the first one, with constant velocity, how does the same physics look to you? That's the whole concept of special relativity. I said you have to do this when walking with constant velocity. That is what makes special relativity special. It only works between two observers who are moving with constant velocity with respect to each other. If one of them is accelerating, special relativity does not work. And you have to go to general relativity. Now, only special today. What do you remember? That's evil. I mean, we just did this 3 weeks ago or so, but still. What do you remember? Just could be wrong, could be right.
There's no preferred frame.
There's no preferred. Okay, thank you. And I'm going to add a little bit more to it. No preferred inertial frame. And the word inertial, if you don't know what that is, don't worry. We're going to introduce it later. This is me just collecting statements, and then we're going to fill in the details. Anything else?
Lorentz transformations?
Yes. There's or the Lorentz transformations. Again, if you don't have exactly clear what everything means, this is exactly what we're going to talk about for the next hour and a half.
Minkowski interval.
Yeah, of course, there's a Minkowski interval. Well, let's group these two together, because when somebody mentions time dilation, you know that somebody's going to say Lorentz contraction, okay? Time dilation / Lorentz contraction. By the slash, do not mean that the things are the same, yes? I mean different things. Just want to group them together in one bullet point. Lorentz contraction. How about the non-relativistic electrodynamics people?
4 vectors are very important part of special relativity.
Yes, 4 vectors, of course. formulas.
Relativistic velocity addition, maybe?
Oh, okay, well, do you know it by heart too?
Maybe.
Okay.
Can you give it a go?
Sure.
Was V plus U over 1 plus V times U over C squared.
Yes, and what is the outcome? What is this thing?
I think they usually call it W or something.
Sure.
U prime.
Or U prime.
Yeah.
Let's give it any name. What does it mean? I think
That-
there's V's and U's added together in some C's.
That you can exceed C's with this.
Well, that is a consequence.
Yeah.
That is very true.
It goes to infinity if you approach the speed of light.
It does not actually.
No.
If you go to the speed of light, it gives you back the speed of light. Now, what does it mean? What's the physics?
It describes how two observers see a certain event if those two observers are moving with a certain velocity with respect to one another.
Okay, it's almost correct, except here what we don't use is the word event. In other formulas, we always use the word event. Over here, it means something like this. If I'm a person, I like to think that I am, and I see something moving there, okay, and I see that thing over there move with a velocity u. Mind you, that thing does not have to have constant velocity. It could be any velocity. Well, that means I measure how many meters that thing moves in how many seconds, both measured by me. It gives you the velocity. I call that one u. I say it's 50 meters per second or something like that. Now I'm standing here looking at that thing. Here's another guy. See consistent. That thing is moving over there. Let's say it's a flying bucket. I have no idea why it's a flying bucket. There's a bucket flying in that direction over there. Somebody threw a bucket. It's 50 meters per second. So quite a muscular guy who threw that thing, okay? I'm looking at that thing, I say 50 kilometers, what did it say? Meters per second. Here's another guy looking at that same bucket, but he's moving with respect to me. Our relative velocity, that is what we call V in that formula. So it's not the velocity of the bucket, it's the velocity of how fast I am moving with respect to the other guy. Now, I'm also looking at the flying bucket, and I'm also going to calculate how many meters that thing flies per second. What I get back is what we call in this formula W. And in electrodynamics we call it U prime, but it means the same concept. Now, as you can see, if this guy sees the bucket fly by with 50 meters per second, and suppose that I'm that second guy and I'm moving in that direction with 10 meters per second, then the bucket should go, what, 60 meters per second, right? Because that thing is moving over there. I'm adding to how many meters the thing moves away from me because I'm moving myself in this direction. So you would think, well, it's this guy's velocity of the bucket plus how fast I'm moving with respect to this guy. Make sense? That would be 60. V plus U, 60 meters. That guy, oh, excuse me, 50 meters per second because that's how fast the bucket flies for that guy, plus 10 meters because I'm moving with respect to that guy with another 10. Gives you 60. And if this were Newtonian physics, this would be correct. It's called the Galilean transformation. It's not Newtonian physics, it's relativity. And relativity tells you, for reasons that we will derive, that you have to divide this 60 meters per second by this other number. And you can tell that this number is necessarily bigger than 1. So you're going to divide the 60 by something bigger than 1, gives you a smaller number. So this is velocity addition. This is Newtonian, this is, for lack of better, Einsteinian. And indeed, some people already know that if the bucket happens to be flying with C, this guy stands here, sees the bucket fly along with what bucket's going to fly with 60, with the speed of light. Let's say it's an actual light ray, 60 meters, C meters per second, okay? So that means that for one guy, U becomes C, and then if you just plug in U and C in this, and you do the math, you will find that W is also going to be C, regardless how fast the other guy is moving. If you don't believe me, we can write it out later. I'm just collecting statements now, but I cannot help myself, I have to mention this. So that means that this equation tells you that it's impossible to see something move with another velocity than the speed of light. If somebody sees something move with the speed of light, then all the other ones do as well. That's what this equation tells you. Again, we were collecting statements. Anything more? Something about energy or something like that? energy masses, momentum, sure, they're all related. So.
Easy C squared. Then.
Oh, there's a nice one. This one only holds at the moment that you're looking at a bucket who's standing still with respect to you. If it's not standing still, get something extra.
It's inertial mass versus relativistic mass.
Yes, that is a statement that people typically use. This is the full formula. If something is moving with respect to you, you're looking at the bucket and you want to know its energy. If it's standing still with respect to you, then this is its energy. If it's moving with respect to you, then this is its energy. You might remember from special relativity that there's a gamma, which is always this factor, which is always bigger or equal to 1. So that means that the energy increases of the thing. If something is moving with respect to you, it will get extra energy. Don't be surprised about this. This also happens in Newtonian physics. Here's a pen. It has a certain amount of energy, maybe, potential energy because of its height. Now the other observer, I'm looking at that thing, the pen is now moving with respect to me. Of course it has more energy now because it has now kinetic energy as seen by me. It still has its height plus kinetic energy because of a relative motion. So that's not special to special relativity, that you can add energy just by moving with respect to something. It also comes in special relativity by this formula.
That is pseudo force. Coriolis force.
Fictitious force. It is not. No. But I mean, when we're going to do the general relativity, I'm going to talk extensively about pseudo forces, or if you will, fictional forces. I mean, we're very grazing the concept, but it's not in here yet. There was a question, I think.
No, just
yes.
So you said that this is the general formula.
Yes.
Or is it not like plus p squared?
Yes. There's another version of this formula. I'm not writing it down anything new. It's the exact same formula. It's just different mathematics. That says, well, what you could also do is take the square of the energy. Then it is equal to its momentum times c squared plus m squared c to the 4th. This is the same equation. You can mathematically very easily prove that this is the same. Again, if you're not picking up everything that I'm saying right now, don't worry, this is exactly the topic. This is just me collecting results. At the end, I'm going to go back to this list and hopefully you will see that you've understood everything. Yeah, there is though one difference, just a subtlety here.
So can you use that for photons?
Oh, well, you can use this one for photons, this ones you cannot.
Yeah.
Because these photons do not have mass.
Yeah, because then the one dog will cancel out
Yes.
and then you can still have energy.
Exactly. No, that is very true. There's another subtlety here. Namely,
This connects energy and momentum. Is that it?
yes, what this one does as well, it's just hidden in the rest of the equation. If you think about it just for a little, the gamma contains the velocity, but times mass says something about momenta, right? Momenta is mass times velocity. So you can already see that this combination, this one, velocity and mass, so there is already some momentum, but it's hidden mathematically. No, the subtlety is this. What's the answer? 2. Just 2? Minus 2. So masses are positive, c squared is a positive, gamma is always a positive. So this is always positive, this equation. Now this equation, if you stick the square root, might give you a minus sign. So from going from here to here, you've introduced new energies, negative energies. There's a subtlety. Now a subtlety we have to concern ourselves with. The only reason I'm bringing this up is because there's a huge misunderstanding with these negative energies. That is that people tend to think that this is antiparticles. That is true. The negative energies have something to do with antiparticles. The fact that you get extra solutions here, the minus 2's, is indeed the way that tells you that antiparticles have to exist, just from special relativity alone. But the misconception is this. It does not say that the antiparticles themselves have negative energy. They still have positive energy. Now how that trick works is not something we're concerning ourselves with in this course. I'm just bringing it up because it's easy to think that you've now understood that antiparticles come with negative energies. They don't. They come with positive energies. If you want to know how that works, that there's a minus solution, yet you have plus energy, well, I'll relay that to maybe some breakdown, and I can give you some details on that. Just bring it up so you don't fall into that trap of thinking that. Anything else maybe about this whole list? Should something be added?
Where is information for the gamma factor in the second equation? Where are you to get the relativistic information?
That's sort of the inverse question of this one, where does the momentum go? The momentum is hidden in the gamma, and the gamma is hidden in the momentum.
Okay.
In fact, let me make it very explicit. This P over here, from classical mechanics, you know that P, momentum, is mass times velocity, yes? In special relativity, it's gamma times mass times velocity. So there is a gamma hidden in here. I hope this gives you some idea that these things really are related. There's no gamma, or there's no P here, but the P is really hidden in the gamma, and there seems to be no gamma here, but it's hidden in the P. It really is the same equation. I think this is about it, really. Now, the rest of special relativity comes down to doing exercises and what happens if you look at something from this observer frame and the other observer frame. All right. Now, again, my goal is to have gone through special relativity in such a way that at the end we can just check whether you've reacquainted yourselves with all these concepts. That's the idea. Now, how to derive these things? What is our starting point? You feel a rant coming up, right? Yeah, okay. I'm going to keep the rant short this time. There's a rant involved. How would you derive these things?
Einstein's 3 axioms, 4 axioms.
What are they?
Well, condensed version of this.
That would be a good way to build up a theory. Just make this an axiom, all of them, all 12 points. Say, look.
Speed of light holds the same for all frames.
So yes, we have to have some starting point. In math, you would typically call starting point an axiom. In physics, you tend to call these things postulates. Don't worry too much about the name; it's just terminology. But you have to have some starting point, and there's a number of starting points, different starting points. They all boil down to the same theory. And here's that rant. What they typically teach you is a starting point where you say indeed something like, well, the speed of light has to have the same value for everybody. And there's another axiom. You have to have 2. So here's one version of the axioms. And speed of light has to be the same for all. Again, terminology, but make sure that you don't say constant, that the speed of light has to be constant. Constant is something, it means something in physics, but it means if you look now and you look a moment later, it still has the same value. Well, that is certainly true for light, but it's not what is meant in its postulate. In its postulate, you say, well, if one guy looks at something, it has the speed of light, then it also has to have the same value for the other guy. That's a different statement. Do you see the difference? It's important.
Lorentz invariant.
That is, if you want to be really puristic about terminology, that is the right one. So let's go with that one. C is invariant. You're right, the official word is Lorentz invariant. I'm sloppy. Skip the Lorentz part. Is invariant. By invariant, again, we mean has the same value regardless of how fast you yourself are moving. If one person sees it move with C, then everybody sees it move with C. Regardless whether you try to catch up on the thing or run the other way, you always go with C. Second postulate.
The laws of physics has to be the same in every inertial reference frame.
Exactly. This is called what we call the principle of relativity. It's not always as emphasized as much, but it's actually the more important of the two. The principle of relativity. What that means is the laws of physics should look the same for all observers. That is a non-trivial statement. I can think of laws of physics that look different for different observers. Does anyone have an example maybe? So I have some formula and it holds for if you're standing still with regard to some experiment, but you have to be moving with regard to the experiment, the formula all of a sudden is changed by something else. Yes?
Example you used with the pen earlier when dealing with kinetic energies.
Yeah, well, that is that's a very good one. Exactly. If suppose that I say, you know what, the energy of stuff is given by suppose that I say this. Somebody told me that that's true. That is certainly true if I'm looking at this pen standing still with respect to it. Now, if I have to be moving with respect to the pen, it will still have that amount of energy, but plus the kinetic energy, because now the thing is moving with respect to me. But do you now see that this formula apparently does not hold for both of these observers? It holds for one of them and not for the other. The principle of relativity says that all of physics you should be able to formulate in formulas that hold for all of them. That do not say you have to be in this particular coordinate system for it to work. In fact, Paul's already said this. There is no preferred inertial system. Relativity says, regardless how fast you are moving or what your motion is, your formula should always be such that you can always use them. So this one does not work. This one, on the other hand, one that we had over there, is. This one is you can use even if you're standing still. If you're standing still, then gamma becomes 1. Here, if you use 0 and gamma becomes 1, you get your old formula back. But it also holds for the other guy. So this one is true in all of these systems. Now, again, the principle of relativity says there is no preferred system from which you have to do your physics. All other systems have to work as well. And that is a requirement. It tells you that your maths has to be written in such a way that it always works. So again, this one does not work, does not agree with the principle of relativity, and this one does. But does the principle say all formulas have to be of this kind? That's the idea. Now this, again, is the usual starting point for special relativity. I was thinking when I set up the lecture series what I was going to do in every lecture to just go through the original derivation of the laws of physics, special relativity, so the Lorentz contraction, Lorentz transformations and such. I've decided not to. Do you know how they go though? If you take the speed of light to be invariant and you want to derive, say, this formula or Lorentz transformations, how would you go about? How have you seen it done?
Mirrors and trains.
The mirrors in the trains, yes?
And the light clocks.
Yes, the light clocks. Now, I don't want you to recall in full detail how the light clock experiments went. You can easily look them up. They're in all relativity textbooks. This is how Einstein himself did it too. But Einstein knew this is just a stepping stone towards a bigger formalism. And unfortunately, because of lack of time and all kinds of didactical reasons, people tend to stick to the light clocks. Here's the rant. Stick to the light clocks. And never make that full step to the rest of physics. And I really want to impress this on you, that if you stick to light clocks and you find these equations, all of them, you've only derived it for situations in which light clocks happen to play a role. You have no business whatsoever finding a result, having used one particular experiment, and I say, well, I'm going to assume that all of these laws apply to the rest of physics as well. This is what we call an induction step, yes, in philosophy, that you have this one particular thing for which it works, and you say, well, I'm going to assume that it holds for the rest as well. You have not proved that. You have proved it for light clocks. So this works, but if you want to do relativity and really build it up in a full mathematical framework, this is not the way to go. It's a good way to get into the stuff, but it's not the way to continue. Now again, Einstein himself knew this. He used this particular set of starting points, but in his article he explicitly writes, he has built in some mathematical fail-safes to tell you that this induction step, assuming that what you find holds for the rest as well, he has actually made that explicit in his article. Again, this is usually the part that's omitted in a relativity course. It's fine, but we're going to do it the full way. For two reasons. One of them is because I'm a purist and I want you to know how things work, and not because you happen to have found one experiment in which it works. But the second reason is, the other version that we're going to start with today will give you the same results, but it will have brought everything back to space and time, without having to say, well, there's a light ray or a light clock or whatever physics. What I'm going to derive does not depend on any explicit details of your experiment. Another way of saying the exact same thing is, if you can do a derivation without having to refer to particular situations, then that means that your derivation holds for all. So I'm going to make it bigger. Never have to make the induction step because I never put details in anyway. That's one thing. The second thing is the mathematics that comes out of my quote unquote my derivation is that it's the exact same mathematics that you have to use in general relativity. That's what I mentioned before. Today is most of the math, the derivation math. Once we have that, you understand how that works. It's only a small step to use the exact same physics mathematical formalism to do curved spacetimes. That's the idea. So here's the second version. By the way, there's also a third and a fourth. It really depends on what your goal is, which one you prefer. But in my experience, if you want to do general relativity, this is the way to go. What's actually already on board? That's the one. Start with the principle of relativity. That still holds. And I mentioned that there's a fourth and a third one, maybe a fifth and a sixth. There's all kinds of starting points. All of them have this as one of them. I honestly do not know of any deeper lying mechanism why this should be true. Maybe a philosopher could say something about that. Well, of course there's no preferred coordinate system. I don't know. So this is something that all these derivations have in common. It's this one that's different. I'm not going to assume this. In fact, I'm not even going to say that there's light in my physics. What I'm going to derive also works if it just so happened that, that the universe was created without any light. This is a statement. The Minkowski line element is invariant. Yeah, what the hell does that mean?
That looks like more intuitive.
This is not very intuitive, is it?
For the first one.
Yeah, this one is, and this one is not.
No, the first one is this, but I'm sure this one's more correct.
It's also intuitive if you think about it. So I'm going to I'm going to try to make you understand that this has its own intuition. I mean, sure, this is something you can easily envision, pun intended, because you know what light is and you see light rays and such. You're used to light rays. And this one has intuition as well. But first let me introduce what I mean by this statement. That means I'm going to introduce what a Minkowski line element is. So we're going to work from this one, yes? Oh, and having done this, I'm going to show that this is the result of this one. So I've not thrown anything out. If you start with this, you automatically get this. So we're back to things being invariant and such, light speed being the same for all. Now, what is the Minkowski line element? Now, this might be the most important statement of the whole course. I'm not being sarcastic here. This is really true. What is a line element? I'm just going to write down the equation. You're going to have to accept it for now, and then I will hope that I can show you why there's some intuition built into here. This is the line element. Again, this is familiar to at least half of the audience because we've done it before. We've also done it in nuclear physics, a small part of it. But in electrodynamics, we really spent some time on this. But it's good to go over this again. It's a particular combination of dt's and dx's and dy's and dz's. Now, what the hell is a dt, and what is a dx, and what is dy, and what is a dz? Well, the thing is this. Suppose that you have two things happening. And Two things happening. Well, if something happens, it happens at a particular location in space, but also at a certain moment in time. Of course, one moment in time, things do not happen in 0 seconds, but take something that only takes an enormously short amount of time to happen. What I always have in my head as just a visual aid is exploding firecrackers. Right? That happens at one particular moment in time and at one particular position in space. Now suppose that you have two things happening, two exploding firecrackers.
There is no chai with
There's no
bottle.
chai with bottle.
Yeah, we did it with Chai in his throwing bottle last time. We could also do the flying bucket again. Let's stick with firecrackers for now, okay? Poor Chai to lift up his water bottle all the time so I can show it. Anyway, what the events were. Here's a firecracker. And let's take another firecracker. This one over here. Two firecrackers. Suppose that both of them explode. Of course, an explosion, if you slow it down and film it, you will see it also takes a certain amount of time. But it's a small amount of time. We're going to assume that the explosion itself takes 0 seconds, by good approximation. We're also going to say that the location of each firecracker is down to the millimeter. Of course it isn't, because there's a certain spatial size. But as a good approximation, we'll say, well, firecracker is small enough, we're going to say it's one particular location and explosion is at one particular moment in time. Now, relativity, special and or general, will not say anything about moments in time and about locations in space. The only thing that special relativity and general relativity will tell you is a duration in time, the amount of time between two moments in time, and the distance in space, the difference between two locations. That's the only thing that special relativity does any statements on. So in order to do special relativity, you never can suffice with only one firecracker, you always need two. Or Chai throwing his bottle around, or flying buckets or something like that. You need two things happening, otherwise you cannot do any kind of relativity. Now you have two exploding firecrackers. This one explodes, and 2 seconds later this one explodes. Then by dt I mean 2 seconds. The amount of time between the two events. That's this number. Now, there's also a difference in their locations, their spatial locations. Again, you cannot do special relativity or general relativity with only locations. You need a difference in locations, and that's, of course, this spatial distance between the two firecrackers' explosions. Now, this distance is what we will call dx. That's about 1.20 meters or something like that. That's our dx. And I hope you can understand that if I would have put this one on the ground, there would have also been a dz between the two explosions. And if I would have put it over here, you would have also had a dy in the two explosions. So in order to understand the difference between two things happening, you need 4 numbers. How far they are apart in time, and 3 distances in space. Those are these 4 numbers. Now this is not physics yet, this is maybe just saying what things mean. Here's the physics. If you take the 2 seconds squared times c squared, and you subtract the square of the distances, some number will come out. And it's this number that will be the same for all observers. Or, we already introduced that word. This is not the physics, yes? This is just a mathematical definition. This is the physics. The number that comes out is an invariant. Extremely important to understand what that means. Firecrackers again. Here's one. Here's another one. Suppose that I'm the other observer. To me there was 1.20 meters in the x direction. dx is 1.20 meters. Okay. Now I'm the other guy. I'm looking at the same 2 firecrackers exploding. And let's say that, I'll walk by, let's say that this one explodes at the moment that I pass this one. Ah, that's that one. And I just keep on walking, pop, 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 and all of a sudden this one explodes at the moment that I pass by this one. how much spatial distance is there between the two explosions as seen by me?
Longer, 0.
I hear 0, I hear longer.
So the explosion happens and then you move away towards the center.
Yes,
Right.
so I walk here, right? Walking, bang, and bang. What is the, as seen in my observer frame, in my coordinate system, how much distance is there between the two explosions?
They both happen right next to you.
Yes.
So it seems like it's
at the same coordination.
Yes.
Yeah.
Okay.
Yeah, I mean, I am my own coordinate system, yes? I'm always in the middle of my own coordinate system. You can imagine this as if I have this x-axis sticking out of me. And at the moment that I pass this one, bang, it happens at my axis 0 position. And walking, that this one explodes, also happens at my axis 0 position. So my dx would be 0. See that? Right. I'm going to skip the dy's and dz's. Let's say everything happens in only x direction, so we don't have to worry about these. But do you see then that if my dx is 0, then my dt should not be 2 seconds anymore, because this combination has to stay the same. For the guy standing next to the firecracker, this was 2 seconds, and this was 1 m². Some number comes out. This principle says that number has to be the same for everybody, also the other guy. But the other guy is dx is 0. Then necessarily dt has to change accordingly. This does not happen in Newtonian physics. If one guy sees 2 firecrackers explode 2 seconds apart, then the other guy will as well, regardless of how fast he is moving. Alright? So already from this statement, the invariant statement, you can see that something strange will happen to time if you happen to be moving with respect to things. Now my claim is, of course we're going to work out all these details with exercise and actually do this in practice during the tutorial. My statement now is just this. This statement, that this combination has to be the same number for all observers, is all that you need to derive special relativity, all of it. No other assumptions are necessary. This gives you everything, including all these formulas, everything that's here is all written in that one statement. The question is how to pry it out. Now, some history. Einstein himself didn't do it in this way. He did it using the light clocks, knowing full well that he derived it for light clocks and made an induction step. And then his former math teacher, he went to the Polytechnical School in Zurich, Einstein did. His former math teacher, Hermann Minkowski, saw this article by his previous student. I said, wait a minute, I think I can write all of this into one mathematical statement. This is why we call it the Minkowski line element. Now, there's one caveat here, and that is this only works at the moment that the two observers move with constant velocity with respect to each other. That's what makes it special relativity, not general relativity. Yes?
So all time dilation, Wallace contraction, all these weird effects happen to ensure that that stays invariant.
Yes.
Space and time will adjust itself to ensure that both observers.
Yes, that is a very concise way of putting it. In fact, it's my preferred way of putting it. Space and time will modify itself in such a way that this number will stay the same. I remember when I did my exam on special relativity, it was part of it was an oral exam, and my teacher, who has passed away since, Hesselink was his name. He said, so can you tell me in one statement what special relativity is? And I used pretty much the same formulation as him, as you now did. Well, space and time modify themselves such that this number comes out the same. So I'm saying we seem to be in agreement with each other here.
Great minds and all that.
Yeah, exactly. Great minds think alike. Any questions so far? It's abstract, isn't it? This part, isn't it? I just give you some weird combination of distances and durations, and I tell you, well, this has to be the same number. Yes?
Could you explain again how the person moving forward between the two firecrackers will perceive them as happening at distance 0? That I didn't understand.
Oh, okay. Sure. Do you agree with me that I am in the center of my own coordinate system? I mean, there's an x-axis sticking out of me, there's a y-axis and a z-axis sticking out of me, but wherever I go, I'm always in the center of that coordinate system.
You're always the origin.
Yes, I'm always the origin. Again, firecracker here, it explodes. I measure where that happens in my coordinate system and say, well, it's next to me, so that's 0. And then I come here, then the other one explodes, and I again look where that is in my coordinate system, it's still at location x is 0.
Imagine a person moving along an x-axis, independent from himself.
Okay, but
That's
then
classical, yeah.
it's not just classical. Well, you could do that, I'm sure.
There's an opposite space and time, and this person is moving with the speed of light to it.
Well, you're adding a couple of things on top of each other now. First of all, the person cannot go with the speed of light himself.
No, I'm correcting my mistake, understand?
Oh, I'm sorry. Oh, okay.
I'll explain my mistake.
Okay, good. So, is there a lingering question still there?
No, no result.
Okay, great.
Thanks.
So yeah, that's the idea. Now, I promise to give you some intuition where that statement comes from. And once I hopefully have given you that intuition, then the next step is to take that statement and derive this. Right? And then you have everything in the right formulation in order to do general relativity starting next week. Intuition. I was hoping that there's another blackboard behind here, but there isn't.
Just use the wall, otherwise.
Yeah, get in trouble. Thomas.
Better than having bio or chemistry on the walls.
You have windows here we can work on.
Exactly.
Can we actually erase it from there? Yeah.
We did during our project.
That is true. Different building, hopefully it's the same window, so the same material. Let's start here and see if I'm short of space at some point. Okay? Let's go to just normal space, no difficult space-times, just an x-axis and a y-axis. Alright? Forget about the time for now, for time components. Suppose two things happen in x-y space. Something happens here, firecracker explodes, and another firecracker explodes over here. Yeah? And suppose that this is x1, this is x2, this is y1, this is y2. Question. How many meters is there between point 1 and point 2? How many meters? Can you think of an expression?
x2 minus x1.
That will be the difference, that will be the distance in x direction.
Or even mathematically
This distance is what I want to know.
the mathematical statement.
Yeah. Can you think of a formula for this so I know how many meters this is? Would it help if I draw this?
Yeah, vectors.
Exactly. So, well, I want to know this number. Let's call it d tau squared. Okay, then you say, oh, well, that's just the x squared. By d, I just mean the difference between the two, yes? The distance between the two. In x direction, and here's the difference in y direction, that's this one. And then Pythagoras theorem tells you, well, then that means that this number is just given by the x squared plus dy squared. Agreed? Just Pythagoras theorem. Okay, keep this in mind for a second. I'm going to do the following trick. I'm going to look at the same two things happening for some other guy. But it's not a moving other guy, it's a guy who just happens to be such that his coordinate system has its y here. And in the other guy's, red is the other guy, the other guy's coordinate system, this is x. What would be his distance for this amount?
Same distance.
It's the same distance? Agreed? Do people agree with that? That in the red guy's coordinate system, where this is not the x-axis but the y-axis, and this is not the y-axis but the x-axis, this is just the same number? But you can easily just write it out by, again, Pythagoras theorem. You get dx squared plus dy squared. So we just get the same mathematics. The formula is still the same. But also you can just see from the picture that if I want to know our mutual distance, right, and I put you along my x-axis, I get a couple, 3 meters out or something like that. But you know what? If I'm going to rotate my coordinate system that the distance has not changed at all. I can easily go to the other guy's coordinate system and still get the same distance between the two of us. You could also say, our mutual distance, or the distance between these 2 points, is invariant. The formula for it does not care whether you are this guy or that guy. The number will always be the same. Does it already give you some intuition? The distances between points do not care whether you are where you have your x and your y axis. Even if you don't stick to 90-degree differences but 24.3-degree differences, sure, the equation will look a little bit more difficult because you have to figure out how exactly where the dx's and dy's are. You would still get the same number out. That's the idea. The only thing that is now new, so this you understand, yes? The only thing that is now new is that Einstein, or actually Minkowski put it in this form, but Einstein realized it conceptually, that if you also want to know not just how many meters there is in between people, but also how many seconds, then this combination itself again is invariant. That if one of these x's is not x or y, but one of them happens to be t, the time axis, then the same idea still holds. Yes?
On the diagram, if you would have to do the same with time,
Yes.
What would be the axis then?
The time axis. How many seconds there is in between the two moments, 1 and 2.
I mean, if it's time, it's against what? You have 2 axes.
Yes.
One of them is time, or
Yes.
2 of them?
No, one of them is time.
What's the other one?
X, Y, Z, one of the 3 spatial directions. You can also understand that if you want to do this, then you have to make a 4-dimensional drawing, because there's a difference in X direction, in Y direction, in Z direction, and now also in time direction, and I don't know how to draw that, so I stick to 2 dimensions. So it's really just Pythagoras theorem, this statement of invariance, this one. It's just Pythagoras theorem, but now instead of just this part, dx squared, dy squared, dz squared, you also have dt squared. It's the same concept. I'm waiting for somebody to say, wait a minute. Except for ... Let me rephrase my question. If I were to make a Pythagorean theorem of time and space, I mean, Pythagorean theorem tells you to take squares and add everything together, right? Mm-hmm. And what we now have is, well, these are added together, right? All come with a minus sign. That's the same thing as adding everything together and put an overall minus sign. It's just that dt does not come with a minus sign. So it's like Pythagoras theorem, except for a switch of minus sign between time and space. It's the same concept, but for some reason nature has decided to put a minus sign there. And actually, you asked me, I think, at the relative electrodynamics course when I introduced the same concept, you said, but why the minus? I don't know what I said, probably physics, reasons. We don't know. We really don't. We just know that this is what nature does. There are some underlying ideas there, but let's just take this as a postulate. So it's really just Pythagoras theorem in 4 dimensions, where 1 dimension has a switch in sign. Otherwise, it's the exact same thing. Now, if you understand, this is the plus-minus kind of sort of intuition I want to give you. I mean, this is quite clear, I think, right? That you can rotate your axis in space as much as you want. Distances will not change. In other words, spatial distance is already invariant. What Minkowski did was say, and if you add time with this extra overall minus sign, then that new thing is also invariant, and that's that statement. Yes?
How come it wouldn't be invariant if all of them were with the same sign? Like,
well, that's a good question. You could actually ask yourself, what happens if you make pluses of these, or all of the minuses, or all of them as the exact same sign, and then do your whole derivation of this sort of stuff, and then check what you will get. I've done that calculation on the train a couple of years ago. I do my calculations on the train mostly, and I did that calculation. In fact, this is my, well, anyway, it's a book that I've used many times before, and I actually wrote it somewhere at the end of chapter 5 or something like that. Just there was some empty space and I had no paper, so I did that calculation just to see what would happen. And it's a longer story than you're interested in maybe now, but if you have them all with plus signs, you will find indeed a world that has rules between time and space. And then it's up to experiment to tell you that these rules apparently are not upheld. So just experiment tells you you are not allowed to put plus signs. But just what the rules are, it tells you that things can go faster than the speed of light. And it has this opposite rule, that if you go faster than the speed of light and you want to slow down, you're not allowed to go slower than the speed of light. Whereas this rule tells you that you cannot go faster than the speed of light. So you sort of get a sort of opposite world, is what you get out. That's a one calculation that I can show you now, but it's an interesting idea, yeah. But ultimately, it is sort of experiment, right? I mean, you take this as a guess, as your axiom, you postulate, you do your math, and then you check whether nature has decided to do it, and the answer is it has decided to do this and not the plus version. Now, one more thing to give you intuition. Perhaps I'm going to take you again as an example, okay? We're going to see our mutual distance. Do you see the guy who's sitting over there is always the guy who's used for experiment. It used to be Chai all the time, but now it's you. Okay, there's a distance in between us. This is my x-axis. Again, I'm in the center of my own x-axis. There's 0 dy now, yes? And there's a certain amount of dx. Now I'm going to move like this. Now the amount of dy is non-zero. The dx is now 0. Do you notice that the total amount is still the same, right? It's still 3 meters or so. But do you notice that by rotating like this, I have turned my x numbers into y numbers? The 3 meters is now completely in y direction where it used to be in x direction. And if I would have taken a rotation halfway, it would have been a little bit of x and a little bit of y, but it's such a combination that Pythagorean tells you it's still 3. The key to the intuition that I want to give you now is that apparently rotating over these axes will change the number x, it will also change the number y, but the combination stays the same. I'm saying that the amount of x is not some holy number. It's only their combination that's a holy number. Why is that important? Because if you would apply the same thing here, you can already tell that if you change your t direction by a certain amount, you do away with a little bit of t. There's less time in between two things, but it has to compensate by more space. Isn't that sort of like this? Time becomes bigger at the expense of space becoming smaller. Just like x is becoming a smaller number now in exchange for more y. This is the whole idea where time dilation, the Lorentz contraction comes from. Yes?
That is it. Just to be sure, so what you're saying is if, for example, we take dx squared and dy and dz and put them all in like a letter b, for example, right? This letter, if you rotate, the value of this letter will not change.
Yes.
But if you take this form, the values of each will change, right? If you rotate.
One more time. Just start over.
All right.
Yes.
The same example you
Yes.
gave us, right? If you rotate from this, for example, the value of dx, dy, dz will change, right?
Yes.
If you combine all those numbers mathematically and call it b, for example,
Mm-hmm.
b won't change if you change because the
Yes.
total add up, right? Okay.
Yes. That's the idea. And you call it letter B, and what I do is I call it d tau. This is your B. Yeah, I haven't mentioned anything about this part yet. For one thing, I smuggled in a c squared here. I had no choice. Because this is a couple of meters, right? This has the unit of meter squared. This is meter squared, that's meter squared. This thing, without the c, will be time squared. And you cannot add things in physics if they don't have the same unit. So you have to squeeze some velocity in. Now, of course, it's the speed of light, but I'm just going to say it's some number that happens to be the speed of light. I could have also written any speed, any velocity would have made sure that the units are the same. It's up to the experiment to decide what number that is. Turns out to be the speed of light. I'm making this point because I don't want you to think that I'm actually secretly squeezing in light clocks. I'm not. I haven't said anything about how I'm going to measure things, or that's going to be a light clock or a bouncing laser ray or something like that. I'm just saying, in order to make the units come out right, a velocity has to come in somewhere. Even if I'm not going to use the phenomenon of that velocity, say light, to do the measuring with. I mean, is that a clear point? I haven't said anything about how I measure things. I just say some speed has to be in there, some meter per second.
Is that also why it's added in the Ames squared equation?
Yes. All right. How are we on time? Again, not a pun, just
Halfway.
Just over halfway through.
halfway through. Is time for a break? Because you can let this sink in and I'm going to derive these things. Is that a good idea? All right.
That's some dedication,
Yeah,
right?
that's tough. Okay.
For an experiment even.
For science.
Yes.
Okay. Now I propose we continue. I hope I've given you some intuition of what this means. Again, the minus sign I cannot really explain to you. This is just, you can either do with a plus sign or a minus sign, and nature has decided to give us the minus sign. Maybe some philosopher knows a deeper reason for this. We can speculate a little bit about this, but we're going to take it as our postulate. And just to already show you where the connection is going to be with general relativity, I made it sound as if the only choice is that there is a minus sign versus a plus sign. Why not just any random number, plus or minus? So it's c squared minus 15 dx squared plus 38 dy squared minus pi times dz squared. Why not? Well, again, nature has decided that this is what we're going to go with, but general relativity is we're going to make the step that these numbers in front of the dx squared, dy squared, dz squared, and dt squared are not fixed. If you're going to go to observers who are not moving with constant velocity, because leaving the special going to the general case, you will find that the numbers in front of the squares change. So generally speaking, here's a number, plus c squared. Here's a number, minus 1, minus 1, minus 1, are themselves functions. And it's when you do that, this is when you enter general relativity. I hope you understand that everything will become somewhat more complicated, because all of a sudden you have to not just deal with how these things change between exploding firecrackers, but also the numbers themselves change along. So that makes life a lot more mathematically cumbersome, but the idea is still the same. Also in general relativity, we will have this as our axiom. It's just that these numbers change. So given a certain amount of gravity, you can calculate, of course we will do this as we go along, but just to give you some idea, if you have a certain amount of gravity, suppose you're hovering close to a planet or some nebula or an enormous amount of energy, there's a formula that tells you what these numbers are instead of c squared and minus 1, minus 1, minus 1. And what these numbers are depends on how much energy and matter there is in that particular piece of space. And Einstein found out what the formula was to calculate these things. Now, we're going to take these numbers today as fixed. I'm going to show you how you can derive these rules. And once you've seen how to derive these rules from this principle, then, well, apart from more mathematical difficulties, the idea is still the same. For general spacetimes, where this is not c squared minus 1, minus 1, minus 1, you can use the exact same ideas, the exact same type of calculation to find what these rules are in the presence of that certain amount of mass or energy. This is why I'm saying all of the conceptual physics, mathematics, is in here. We've already done it. Just applying it to more difficult situations is where life becomes more mathematically troublesome. No worries. Special relativity, just for today. This is c squared, is going to stay c squared. This is going to be minus 1, is going to stay minus 1, minus 1, minus 1 for today. And from next week onwards, different numbers. Same idea, different numbers. I will say one thing though. one thing that will happen, regardless in how strange the numbers are, it will always be such that the number in front of time is going to be a plus and the other ones are going to be minuses. That will stay the same regardless of how curved or how much energy or matter there is. This is what we call the so-called Lorentzian signature. The signature, not as in that he wrote his autograph because he was famous, the signature as in the business that deals with what sign should be there. The signature. It tells you, I just realized that myself by the way, regardless of how much energy and matter and how much black holes there are, doesn't matter, there will always be a plus number here or a minus and minus numbers here. Now, depending on which lecturer you have and what book you read, some authors prefer to make this one the minus sign and make these the plus signs. That's just a matter of convention. I'm going to stick to this convention, where this one has the plus, this one has the minuses. But again, regardless of how many black holes and energy and matter there is, and even regardless of which lecturer or author you happen to be listening to or reading a book of, they will always have opposite signs. That Lorentzian signature will always be the same. Okay, now, having said that, let's derive some physics. I'm going to erase this. This is going to keep because I would like to point back to it later. The first thing we're going to do is give a physical interpretation to the name of this number, right? You have this combination, some number comes out, and this thing, we just call it d tau. You call it b, I think, in your question. Well, the official name is d tau. Some terminology, some people just call this thing the line element, Minkowski line element. Some people call it proper time, some people call it eigentime. I don't care about the name, I'm probably going to use proper time from now on. And by proper time, I mean the number d tau. And I'm already telling you that apparently it's a time. It's an amount of time. You can tell by mathematical reasons alone, right? Even regardless of physics. I mean, if this is meters, and here's something times the velocity squared, then d tau squared should have been a time. So d tau squared is time squared. D tau apparently is a time. The question is, what time is it? Not what time is it, but whose time is that? Yeah, it's called proper time, that's true.
When dx, dy on dz are 0.
Yes, you can just read off, right? You can just read off that if dx, dy, and dz happen to be 0, now you can just drop the c squared and drop the square. You would just get d tau is dt. So that already tells you, well, d tau is an amount of time. It's not a moment in time, it's duration between two things happening, two exploding firecrackers. But only in the case that the two firecrackers explode at the same position. Because only then is dx, dy, dz squared, and you get d tau equals dt. Now to put that into hopefully some visual demonstration, here's my one firecracker, here's the other one. Same example as before. And this guy standing here looking at this thing, it explodes. I record where it happened, what time it happened. I wait 2 seconds, then that one explodes. Again, measure where it happened, how many seconds later it happened. I get my dt and my dx, and my dy and my dz. Now, for me, 1 meter 20, I think I said before, apart. And this was 2 seconds. Well, you do the math, you get some number out. Here the other guy comes along. That was the second guy, right? The guy with his, in the sense of his coordinate system. He walks by. This one explodes. Walks happily here, and he happens to be walking with that velocity that makes this one explode at the moment that he passes this one. Now this one explodes. Again, in his frame, in his coordinate system attached to his body, there is dx is 0. For him, it happened at the same position, namely right next to him. So for that guy, dx is 0, dy is 0, dz is 0, and the number that comes out is dt. So apparently d tau is the amount of time that he measures between the two explosions. So what is proper time? What is this thing that comes out? It's the amount of time that passes for that one observer with respect to whom the two events happen at the same location. It's a long sentence, isn't it? So let's write it down for future reference. V tau equals the amount of seconds, the amount of time between the two exploding firecrackers. Let's use the right terminology, events. Between, but now as measured for that one guy who sees them explode at the same location. And see by observer who sees events happen at the same position. So that's what the thing means. You can just easily read it off from this line element. So that's proper time. And I think history says that proper times comes from French, as in propre. It's a clean time. It's the time for that guy who's not messing around with space, walking around while things happen. No, literally, this is where it comes from. Yeah. And then they sort of Englishize it. Is that a word? I Englishized that word myself now. They sort of Englishized to proper, became proper.
Anglified.
Is that the word, to anglify?
I think so, yeah.
And now we're stuck with the name. It's called proper time. Or called clean time, I mean, whatever you call it.
Proper can be translated as my own time.
Yes.
Eigentime is actually the same as proper time.
Yes, I mean, yes. Eigentime, I think, you know, because it's so close to the German word, I can fully understand. It's my time.
Yeah.
Yeah.
Proper
But the
time
French
means the
is
same.
You can say clean, but that's proper.
The proper,
Oh, really?
if it belongs to
Oh.
you, yeah.
Okay, thank you. Now that clears up something for me as well. You could say it cleans it up for me. Yeah, I'm not here for my humor, okay? Okay, but thank you. I did not know that. It was told to me by some professor, the story that I just told you, so I was just lying. But thank you for correcting me.
I didn't pay attention to it. She actually pointed it out. I was like, oh yeah, it means that's
Okay, well, okay, then in German you would call it Eigenzeit or something like that. But we're stuck with the name. It's called proper time or Eigentime. All right. Now again, we're going to do the firecracker things again, and I'm going to stick to my same experiment here. By the way, I said I wasn't going to do any experiments. By this I meant, right? Remember that when I said that? I'm going to derive it without doing experiments. Now note that I'm not introducing an experiment. I just say two things happen, and there's one person looking at the other person looking at it. What I meant before was, I'm not going to say how they measure these things. If they actually took a telescope and looked at these things, or that they had some microphone listening to when they exploded, because that will introduce all kinds of experimental details that I don't care about. Okay? So when I say I don't do any experiments here, I don't mean sure, I still have a situation, but I'm not going to go into the experimental details of the situation, just to be sure that I meant that. Okay, so here's my situation, 2 exploding firecrackers. Again, one guy is looking at this thing, he sees them explode at the same position, all right? Okay, so what he will measure, we saw that, is exactly this number. He sees the 2 firecrackers explode at the same position. How many seconds will that take between the two firecrackers? That's going to be d tau. We saw that before. But now this principle comes along. The other guy, who does not see them happen at the same position, should get the same number out. Now for him, we cannot write that dx, dy, dc is 0, so we have no choice but to write everything out in full. Now, what I'm going to do, Well, I can make it. Well, let's keep it general. I wanted to forget about the y and the z directions. Let's make it general. Let's put everything in there. Now this here is that principle. The number that comes out should be the same for both. And now we're just going to play around with the mathematics. We've put the physics in now, this principle, the rest is just math. Then we get to some solution, some final answer, and we're going to take that final answer and then go back to physics to see what it means. The amount of time between the two explosions for any other person is going to be called dt. And my question is, I would like to know how many seconds this guy sees versus how many seconds that guy sees. Now the answer is going to be time dilation, the formula you might know by heart, but let's see how we get there. Again, this is just mathematics. I'm not going to put any more physics in. I'm just going to play around. You know what? Just algebra. I've taken 1 dt squared out of the brackets. You know what? Let's take a c squared out as well. Again, algebra, no physics.
So it's dt equals this.
It's c squared, d tau squared equals this.
But you move them to the other side. Or?
Yes. But if you multiply this back into the brackets, you would just get this expression back. So it's just mathematically the same. I haven't done any physics. But now I see something happening here, because the x squared, the y squared plus the c squared, just pluses, is Pythagoras theorem, yes? It's the total amount of distance in any direction. We already saw if the x's, the y's, and the z's doesn't care about what direction you're looking at. So let's just call this the total amount of distance between the two exploding firecrackers. And what I see here is, well, here's the c squared here. What I see here is the total amount of distance squared between the two firecrackers divided by how much time there is between the two exploding firecrackers squared. Or let me just put it in words. Distance squared divided by duration, the amount of time squared. Question, how would you call a distance divided by the duration of time?
Velocity.
Velocity. But now squared, because both of them come with the square, so it's velocity squared. Let's call that v. 1 minus, so this is v squared. Well, you have to divide it by c squared, because that was still there. vc squared, and you know where this is going, right? With a combination 1 minus v squared, c squared. Question. It's very easy for me to write down, distance divided by duration gives you velocity. You always have to be very sure that you know what symbols mean in special relativity. Whose velocity is this? Of the velocity of what is this? It is a velocity, but whose is it?
Is it the relative velocity between
The two observers.
Yes, but how that is very true. If only because we know that that's going to be the v later on. But I mean, is there any way of visualizing why that is the case? It is true, though. This is the relative velocity between the two observers.
Because your x, y, and z is your relative distance between the two observers.
No,
right?
no. This is the relative distance between the two events.
Oh.
Again, this is why you have to be extremely careful on special relativity. What do things mean? This is not the distance between the two observers. This is the distance between the two exploding firecrackers.
Oh shit! Yeah. I don't know. What are you saying?
But how about this? What if I tell you that in this particular setup, the distance between the two exploding firecrackers is the distance between the two observers? It's not generally so, but in this case it is. And while you think about why that is true, let me just redo the experiment. I'm this one observer, the one that measures d tau, right? That was the guy, bang, bang. Okay, how much space is there between the two pangs for me? That's going to be 0. Now I'm the guy for who the two things do not explode at the same time. And I'm looking at the other guy walking by. Do you see that in those couple of seconds he has moved from this position to that position? For him to see this one explode, the other guy, I'm standing still, the other guy walking by, the one who measures d tau, for that guy to start here and end up here, he has to walk a distance between the two firecrackers divided by the amount of time between the two firecrackers. Agreed? So me looking at this guy, seeing this one explode and that one explode, and moving just so that he is here when the time the second one explodes, that distance between the two firecrackers is also the distance that the guy walks with respect to me. So generally speaking, dx here, or dy dz, is the distance between the two exploding firecrackers, and in this particular setup, it's also how fast the other guy apparently is moving. And that makes, indeed, this v that I've introduced, the relative velocity between the two observers. Now let's clean up a little bit. We can do away with the c squared, and we can also do away with the squares. And then I will get that d tau is right. I've taken the square root to get rid of the squares. Remember the square root of the 4 equals 2, but also equals minus 2. I've made a choice here. By taking the square, I could have also written down minus this. I'm going to discard that mathematical possibility, because that will mean that if one guy sees 2 seconds explode between the two firecrackers, the other one sees minus some number. That means the firecrackers would have exploded in a different order. Now you might think, why is that an issue? Well, if you think about it a little more deeply, suppose that this firecracker explodes because the first one exploded. You would have broken causality. Then apparently, what is the cause, which is the effect, you have mixed up. You can of course ask the question, so what? Let's take the minus solution seriously. You can work that out. For instance, on a train maybe, in the backside cover of a book. And then again you run into trouble later on. So yes.
Causality is preserved.
Yes. By choosing the plus sign here, we preserve causality. In order for causality not to be preserved, d tau and dt have to have a relative minus sign. Now, I've deliberately chosen not to have a relative minus sign, so I preserve causality. And I don't have to worry about this thing becoming minus itself, right? Because this is always positive. So I've preserved causality with my choice. Now clean up a little bit more, and this is our final expression. We see that the amount of time between two exploding firecrackers is given by this formula. I've just put the square root at the other side because this is the conventional way of writing it. So this is just math. Again, I've made a situation, but I've not said that I should have a light clock to do this experiment with or something like that. Instead of firecrackers, I could have also said, well, here's a guy jumping up and down, here's a guy jumping up and down. I could have also said, Chai is lifting his bottle up and down. I could have also said there's a flying bucket around. Just something that happens here and something that happens there, regardless of how you measure this. So this result is very general. Now, you have to be extremely careful what things mean in these formulas, and we've seen this in this case very explicitly, but just let me write it out. And I advise you to make sure that you have this as well, that you have this somewhere for once and for all. D tau we saw before, that's the time between two events for someone standing still. And by standing still, I mean seeing the two events happen at the same position. Some standing, that's not correct. Time between events for someone who sees them at the same location. And this one, the time between the same two events, but now seen by somebody who is not standing still. Let me rephrase. the time between the two events as seen by somebody for who the two events are not at the same location. Time between the same two events, same exploding firecrackers, who does not see them at the same position, who does not see them at the same location. So this is what these things mean.
So one is faster than the other, always.
Yes, that's a very good comment. I promised that after we've done the math, we would go back to the interpretation. So let's take your question as the starting point for this. This thing, of course, you recognize as the gamma factor, right? The Lorentz factor. So this is just the definition of gamma. And we know that gamma is always equal to 1, or it's bigger than 1. You can see that right here. Now what does that mean? That means that dt is always going to be a bigger or equal to number than d tau. That has physical interpretation. By the way, this is what I meant before, yes? We've done something to our coordinate system. We went to another coordinate system, went from one guy's perspective to the other guy's perspective. We introduced a certain amount of dx, because we started with dx is 0 for one observer. We put in another dx for the other guy, and then dt has to compensate. This is the amount of compensation that dt has to do. Now let's interpret this. For whom is time going fastest? Interpretation question.
The person who sees both events at the same position.
Is his time going faster?
Yeah.
I'm not sure if you could say that. Just
Well, according to him,
Yeah.
time of the
Oh,
other.
sure. There's a twin paradox involved here somewhere. Okay. Good point. Let's not walk into that trap for the moment. Now, let's put it this way: whose amount of time is the bigger number?
That's the one who doesn't see them at the same time.
Yes,
Mhm.
the dt number is a bigger number than the d tau number. So, if you ask them both how many seconds were there between the two exploding firecrackers, one will say 2 seconds, the other will say I saw 5 seconds. So, according to which of the two the firecrackers were exploding more slowly? Was that the 5-second guy or the 2-second guy?
Oh yeah.
Whatever is not the intuitional answer.
No, that's not how relativity works. No, you can reason your way through this. So suppose that I watch you do a couple of push-ups. I have no idea why I come up with push-ups, but suppose you do a couple of push-ups. And I ask somebody how long it took him to do 10 push-ups, and the guy says it took him 2 seconds. And in my observer frame, it happens to come out to be 5 seconds. Now, who of the two saw Panos do the push-ups the fastest? The 2-second guy or the 5-second guy?
Yeah, 2 seconds.
The 2-second guy, okay? So apparently, if I take Panos' push-ups as a clock, I say, well, every time that he does a push-up, I know how much time has passed. His push-up clock is going faster for the 2-second guy than for the 5-second guy. I have no idea why I took push-ups.
Is that kind of like using light clocks?
No, because the light clock actually used the properties of the clock itself. I just happened to take you as push-ups, but I'm not using your muscular frame or how far the ground was.
Any event.
Yeah, just any two events, and just for illustrative sake, I took push-ups. So this is why this is a general result. It doesn't stick to light clocks or to your push-ups. It applies to all. So this is a bigger number than that one. So this guy sees the process go slower. According to him, it takes more seconds for any process, push-up, whatever, to be completed than for this guy. So this is how you have to interpret it. The bigger number is the guy who has the biggest number is the guy who thinks that the thing goes slowest. That's the idea.
So the perceived time the same way, but it's just that the process happens at a slow rate, or no? But the process is how you determine time.
Yes.
Oh, yeah.
Yes. That is a very good comment, by the way, because I once tutored a philosopher on relativity. He wanted to write a book on time, and he had a chapter on what Wittgenstein said about time and what Kant said about time, and then he also wanted to know what physics says about time. And somebody passed the task along to me, so I tutored him for a couple of months. And Sunday afternoons, he always says, "Yeah, but is time really going faster, or is it just a process that looks slower?" And I said, "There's no way of telling."
Yeah, there's no objective time.
No, I mean, you in order to measure time, you have to look at any process. I mean, I took yours, your push-ups, but if we actually had put this clock next to you, that clock too is 2 events that now take more seconds. Every event, 2 events, will take more seconds. So that means, as far as you can tell, time really does go slower. Now, let me be very clear. What I do not mean is that time really just ticks at its own rate. It's just by some optical illusion that it looks as if it's going slower. Now, if everything here is going slower, and there's no way to tell, by no process whatsoever, what is happening there, then apparently it must be time itself. If you can apply this rule to everything, it cannot be a property of any particular process. It must be a property of time itself. There's no, yeah, but what about the real time? There's no real time. There's just any process that you use to measure time, and everything goes slower. That's what it says. That's the idea. Now, the Lorentz contraction, I did this with the relativistic electrodynamics course. I made this an exercise. It's the same type of reasoning, but now to measure lengths. And I have 2 different varieties to get to the same result. Now, a couple of minutes left. What I've done now, if I've said, well, there's a relationship between one guy's time and the other guy's time that makes sure that this one is invariant, right? There was a beautiful statement, nature, what was the statement again? It was something like, nature always tries to make sure that it is invariant or something like that, or modify space and time.
Modify themselves so that stays.
Yes, exactly. Yes. Now again, this is our postulate, and then you can ask the question, well, this one apparently does it. We've just derived that this one makes sure that the line element is invariant. Right? We took the line element invariance to get this, so this one makes sure that the line element is invariant. Are there more general rules that do this? Is this the only relationship between times that make sure that this is the same for all? The answer is no. The most general rule is already on the board here. That's the Lorentz transforms. Now, I'm just going to write them down, and it will be up to you, just as a mathematical exercise, to show that this really is a rule that makes sure that this is the same for all. This is something we will do in the tutorial lecture at the moment. So let me just write down what it is. I have to erase this. This is a good thing about recording, so you can see it on YouTube later. Now, one we've already seen, by the way, right? If I just leave time unchanged and I just rotate myself, make my x-axis my y-axis, that also works. That's called a rotation. That's not the one we're interested in. We want to know how time changes and how space changes. So the kind of trivial x goes into y, let's forget about those. Let's do the most general one that involves time. And that is, of course, the Lorentz transforms. Again, you can derive these by light clocks. I'm just going to say, here's a mathematical thing that makes sure that this rule is obeyed. Here's a mathematical thing that makes sure that that rule is obeyed. You take one guy's amount of time. Oh, forget about the squares, excuse me. That's just habit. I'm just going to give you the solution, and it's up to you to show that it's really true. Now let's play around with the C's again. This is one of them. Maybe write them down first, then we'll talk about it for a bit. Here's another one. Here they are. These are the famous Lorentz transforms. Now, I'm just giving you this as a mathematical statement. If you do this, then this rule is obeyed. Now, let's put some physical interpretation to this. What it says here is this. Suppose you have again your two exploding firecrackers. But in this particular case, again there's going to be two observers. They're going to have a relative velocity v. V is still how fast the two observers are moving with respect to each other. But none of these two observers will see the firecrackers explode at the same location. So they're both moving all kinds of directions. And unfortunately, in their own stuck to their body coordinate systems, the firecrackers will explode at different positions for both of these observers. And for one observer, the two firecrackers explode a distance dx apart and a couple of seconds dt apart. And you want to know but how many seconds and how many meters is there for the other guy? dt primed, the other guy, dx primed, the other guy. Write out these equations, you will get your answer. Again, so you have everything complete. Suppose you have two observers, none of which see two events at the same location. One observer, one of the two, the one that does not have any primes on his coordinates, one measures dt dx, two firecrackers, how many seconds in between dt, how many meters in between dx. The other, which I'm designating with primes, measures the amount of seconds is dx primed and dt primed and dx primed, different numbers. And the velocity between the two, the relative velocity, between the primed guy and the unprimed guy. That number we call V. There you go. So you know what everything means. Then the Lorentz transforms tell you if you know these two numbers, these two, you can calculate what the other has measured. That's what they do.
Why does it matter that none of them see the...
Well, suppose that one of them does see them happen at the same time.
There will still be different velocities between them. So
Between the two
observers.
Yes, that's true. But I mean, this is very general. This rule works all the time.
This is even more general than relative velocity between them.
Yes. In fact, let's see what happens at the moment that one guy. It's very general, so it should also hold for a previous situation where one of them does see them happen at the same time. What is the dx for that guy? The guy who sees them happen at the same time? At the same location?
Should be what was the what?
Okay. This is very general, so it holds in all situations. Let's apply this to our previous situation where one of them did see them happen at the same location. What would that guy's dx be? That's the question. 0?
Yeah, 0.
0, okay. 0. Put your hand here. What do you get back? Yes, you get his time. But doesn't the equation look familiar now?
That's the time dilation.
That's the time dilation formula I had before. That I derived by explicitly saying that one of them was standing still. So what I have here, the sarcasm is strong in this one, but okay.
It wasn't actually sarcastic.
Okay, that was
it
really,
was genuine.
okay, good. So our previous situation, our time dilation formula is actually already in here. Just apply the general formula to the case where one of them sees it happening at the same time, you get your time dilation back. Lorentz contraction, same thing. So this is a general one. So in case of doubt, am I allowed to use time dilation? Because you can only use it if one of them sees things at the same location. If you're not sure if this is the case, you go with these. These always work. Now, Now, one of the exercises is just to show that this indeed agrees with this postulate. Now, my plan for the tutorial is just your basic special relativity exercises. Here's two exploding firecrackers seen by one guy to have these numbers. What does the other guy see? Now, you might have done these things at length in your special relativity course, but again, everything that we're doing now, with only little modification, we're going to use for general relativity as well. So it's really imperative that you get yourself reacquainted with this. Not just to get you the full package, general relativity and some special, but you need this stepping stone to get to general relativity. So let's do some exercises with these rules in a moment. I think this is right on time, aren't we? Okay, great. Any questions for now?
Do you know if this lecture is empty afterwards, so we can actually stay here?
What does the schedule say that we have to go to?
To
Oh, that one again?
On the third floor.
I'm happy. I have no idea if this is empty. I'm happy with staying here. We can also go to the other. That's the one upstairs, right?
Yeah.
Yeah.
We could
yeah,
always-
it might be a little bit full.
3.043 something.
So, what would your preference be?
You can try, yeah.
Yeah,
we could
It's
stay
unlucky
here
that
if
there's
someone
like
comes.
another lecture.
Yeah, let's do that. We also did it with electrodynamics.
Yeah.
Right? Just stay here, see what happens. Hey, just to see if we can strike away. This one we saw. This is the principle of relativity. The Lorentz transformations, you can prove for yourself that these hold. Minkowski interval we've done, there we go. Time dilation, Lorentz contraction, we have done 4 vectors. Well, we have. It's just I haven't made it explicit yet, but don't worry about it. Okay, we'll see that next week. Same with these. It's a very easy step next week because, again, the mathematics I'm going to introduce for these, we're also going to apply directly for general relativity. So if something moves close to some galaxy or something, you can also calculate for yourself what the expression for the energy will be. But that's for next week. So I think we made good progress. All right, let's have a break, see if we're going to be kicked out. If not, do some exercises.